Now, please recall we have our final test in the assessment period of next week. There is a non-assessment period in week 9, and I believe you're only here for half of the week anyway. We will continue on with cosmology. Even though we cannot physically fit it into the timeline, there might still be some questions about the Big Bang, origins of the universe, Hubble's constant. These are things that you need to be aware of. The timeline of the universe and when stuff happened. We're going to go through that. I'll give you a booklet. That's after the test. So the test is going to be everything Unit 4 except cosmology. So it's all the way back to when I proved to you that light was a wave, Young's double-slit experiment, refraction, reflection, polarization, blah, blah, blah. Okay, so all the way back to then. Now, this poster is the all-important poster standard model of fundamental goodness. It is the most current, and it's up to 2000 it was printed and hasn't really needed to be changed since then. If you Google image search standard model, this is one of the biggest posters. It's made by a pretty decent company. It's got that lovely classical black background. The Physics Student Society purchased one and put it up in the common room at Murdoch University, and it was about that size. It was the biggest one that we could find. It's just got lots of lovely stuff. And we will endeavour to go back to this poster from time to time and look at certain things. Now, at the moment, everything is a little bit weird looking. You've got mass that's given in giga-electron volts divided by c squared. And that's what I'd like to quickly touch on. If you could just go to the front of your page right here. So we've got some room on the front. This is what Einstein said. He said that E equals m naught c squared. He basically said that your matter and energy are manifestations of the same thing. All right, so we can turn matter into energy, we can turn energy into matter. Okay, so with that in mind, we can write the rest mass of an object as E over c squared. And so instead of writing joules, remember we said a joule was too big of a value. When we're down to the atomic level, we need EV, kilo EV, giga EV. Now we're up to sort of mega and tera EV. Okay, so now we can have a unit of MeV on c squared. That is a unit of mass. Okay? And so if you see ever a unit of energy divided by the speed of light, that's just Einstein's rearrangement of his equation. What that also tells you is it tells you how much energy you need to be able to produce some of these particles. So, for example, just a moment, Justin, the rest mass of an electron is 9.11 times 10 to the negative 31 kgs. Which we might wish to then convert to atomic mass units by timesing it by 1.60 times, no, not that one, 1.67 times 10 to the negative 27. That would get us into atomic mass units, which I can't remember what number it is. No. A proton and a nucleon is around about 1 atomic mass unit. Remember, an electron is about 1,200 times smaller than that. And then if you recall, in year 11, we go, well, hang on, binding energy, if we did a little conversion and multiplied by 931.5, but really to 3 sig fig it's 931, we get that the energy of an electron is 0.511 MeV per c squared. Okay, now I've forgotten that last step here. It's something like 0.00555 or something. I can't remember.
Do you divide it by 1.67?
You do divide it, sorry. I might have said multiply, but let's go divide. What do you get? What number?
No, I'm just wondering, is the M mega? Yeah.
Mega, yes.
Yeah, it's 0.00054.
0.000545 atomic mass units. Recall this one, that came from chemistry. Remember they said, let's take a gram of carbon, 12, and call that 1 atomic mass unit. Okay, or as 1/12 of that. Sorry, 1/12 of the mass of a carbon-12 atom. And it's close to 1. And then in year 11 you would have gone, well, hang on, why is a proton and a neutron heavier than 1/12? Shouldn't 1/12 of a carbon mass atom be 1 proton, which is 1? And no, remember on its own, they're heavier because when they're combined, what happens? Mass. Exactly. Energy, mass is converted into energy, the binding energy of the nucleus, which keeps everything hunky-dory. Okay? So, that number there, 0.511 MeV per c squared, that is how your particle physicist would measure the mass of an electron. They're not going to go to your data sheet and go 9.11 times 10 to the... Nor are they going to go 0.00545. No, they're going to say, how much energy do I need to make this bad boy? What is its rest mass in terms of energy? Let's go back to our friend, the poster, and let's find... Oh, there he is. Electron. Now, ignore the table. Ignore the title of the table, at least. Here's my electron. Thank you very much. Oh, unfortunately, we need a range that covers a bit heavier particles. So in GeV, move the decimal 3 places, boom, 0.511 MeV, or 0.000, bless you, 511 giga-electron volts. So that's what they figured out. If we have enough energy, we can make matter, which is pretty cool, because at the moment, we're up to the tera EV, and so we're making more and more heavier and exotic particles, okay? So, let's get started, shall we? We shall. Now, it turns out, in order to explain the current model of particle physics, we need to try and categorize our particles. This is getting close to biology, Mr. Salter, where we like to classify things in a dichotomous key. If they've got a certain characteristic, we put them on this side, and if they've got another characteristic, we put them on that side. All right? Unfortunately, it gets a little bit weird when we look at mesons. But anyway, the first split is, are you a particle that has matter and can be detected? Or are you one of these force-carrying particles? Now, the force-carrying particle is named a boson. So you're either a boson or you're something else on the next page. It was proposed by Satyendra Bose in 1930. He worked alongside Einstein, and he looked at these particles. Now, this was the tricky thing. They're difficult to be detected because they're involved in transferring forces or mediating forces. So the bosons are the force-mediating particles. And the easiest one to describe to you is the electromagnetic, because we've already discovered that electrons and photons are interacting with each other when we looked at the photoelectric effect. So, for example, the electromagnetic force is mediated by the photon. Wouldn't you know it? So there's a little gamma for the photon. Gamma for now. So, these guys here are actually long-range forces, gravitational. Then the other two are very short-range. Now, I'm jumping all over the place here. Let's just go back to the top diagram. The ones that mediate force, there are 4 known fundamental forces in the universe. The electromagnetic, gravitational, the weak nuclear, and the strong nuclear. So the strong nuclear binds the electrons together, and then the weak nuclear is responsible for weird stuff like beta and alpha decay. Up here is a diagram. Now this is a Feynman diagram. My favourite physicist, Richard Feynman, in the 1940s and 50s, came up with a simple diagram that helped explain not only the simple interactions, but much, much more complicated interactions. We will look at Feynman diagrams later in the syllabus, later in the course. It's not in the syllabus, but if you can explain a Feynman diagram, it can help you understand bosons and W positives and W negative gauge bosons that we're going to look at. So, have a look here. Time, we move upwards on the y-axis, we move forward in time, and then we just pick an arbitrary spatial dimension along the x-axis. What this is showing, two electrons coming together in space, not that way, two electrons coming together in space, and then we know that they would exert a repulsive force, they would stop, and then they would accelerate away from each other. They would recoil. That's what this diagram is showing. But Feynman added some rules about how these diagrams work, and actually this should be tilted up slightly because moving that way would assume infinite speed. But anyway, look what happens. They come together and a photon seems to be spat out. Now the great thing is photons have momentum. So not only can they impart momentum, but they can also exert a force, and we call that the electromagnetic force. In year 11, or now it's in year 12, we can quantify that. It's equal to k q1 q2 over r squared. We know the inverse square law. At this point, I'm going to stop and show you a minute physics video that has a financial application of the virtual photon. Oh, by the way, these photons are called virtual because you cannot actually detect them. Because have a think, there's a very fundamental process going on here. There's a transaction from one electron to another. And that photon is emitted from one and then captured by another. That is what enables the recoil of both electrons. And Isaac Newton, action and reaction, he was thinking about the right thing, but he didn't know that there were these tiny particles that can't be detected. The reason we can't detect these is because if I had an electron there and an electron there, and I suddenly put my head in between, then I wouldn't see a flash of light. Because that flash of light would then be smacking into my eyeball, and it wouldn't be taking part in the process of mediating the force. So we don't know how many photons are being shot out like a machine gun. We don't know the wavelength of each of them or the momentum, so not like the caliber of a gun, but we know there are bullets, and firing the bullets is responsible for mediating the electromagnetic force between these two leptons, or electrons. Yes, Marcus, I can see you pensively in thought.
Well, so can these photons like go through matter? Because if you had one electrical object below the desk, one above, they'd repel, so photons get traveling through the desk.
Yes. You've just spoken about the permeativity of matter, which is mu naught, or mu of whatever. Basically, different materials can affect how electric fields permeate through. So, yes, but go and learn that at university. But I like that you're thinking about it. I like that. Yes, Mr. Rahal, you can have 10 seconds.
In that case, why don't the photons pass through your eye and still interact?
Because the permeativity of the space of your head is going to prevent electric fields traveling through your head. You are opaque.
Could we use a detector that can do that?
No. Good. I like your questioning, and I'm not sure if I even know some of these answers. But let's get to this video now.
We know the universe has stuff in it called matter that takes up space, and the universe isn't just static. Things happen, too. To be more precise, matter interacts with other matter, like the pull of the Earth and the Moon on each other, or the mutual repulsion of your feet and the ground. We might think that these interactions are just traffic laws imposed by an obtuse pan-galactic regulatory committee, but in fact, the real answer is much deeper and more bizarre. Interactions happen simply because you, and by you I mean the universe, can measure things differently in different places. But wait a second, regardless of whether I measure a person to be 6 feet or 183 centimeters tall, they're still the same height. So measurement, by itself, is meaningless. But as surprising as it sounds, that meaninglessness is exactly what causes the fundamental forces of nature. Now, frequently on Minute Physics, I use analogies to help simplify complicated physical phenomena while still getting the essence of the point across. But today, we're going to witness a real live application of the theory behind the Standard Model. And while for simplicity's sake, we're going to ignore quantum effects and apply it to economics instead, this is literally the same math as the Standard Model. Ready, set, physics. Suppose, for example, that I gave you $2 for a $2 sheep. Nothing has really happened, or no value has been transferred, because I could sell you the sheep back and end up with my same $2 again. Ignoring the fact that I may like sheep more than money, which is why we trade in the first place, the real value as measured by our valuometer, which we call money, is unchanged. What's more, the amount of money we pay for things is really an arbitrary scale, which is obvious when you remember that different countries have different currencies. But of course, countries can't interact financially without converting the way they measure value. So now suppose I want to buy a sheep in Canada. There are two things that'll affect the price. First, Canadians may just value sheep less than I do. And second, their dollar may be different from my US dollar. So perhaps the sheep will only cost $3 Canadian. Which of course means I can go to Canada, convert my $2 US to $4 Canadian, spend 3 of them on the sheep, and come back to the US with my sheep plus $1 Canadian, which converts to 50 US cents. If I then sell the sheep back to someone in the US for the $2 it's worth, I'll now have $2.50 instead of $2. So I made money just by buying and selling a sheep. This is very different from the case of buying and selling a sheep inside the US, where no real value changed hands. Here, just by making a currency exchange part of my sheepish journey, I was able to transfer real value from Canada to the US. And this transfer of value happened solely because we measure value differently in different places. It's like stealing, only legal. Now, don't all go running off to buy Canadian sheep and sell them in the US. In the real world, shepherds and money exchangers realize that they're losing out, and the price of sheep and Canadian dollars will adjust to take this into account and minimize all transfers of real value, or stealing. But making money from nothing does happen if you can act before the market adjusts. It's called arbitrage, and anytime it's possible, it means that the economy isn't in an equilibrium or optimal state. So much for the invisible hand of the market. But anyway, in physics, this effect of moving real value is called momentum transfer, or in day-to-day terms, a force. And now we'll see why. Suppose instead of one border and one exchange rate, we have a whole row of countries that can each exchange money with their neighbors. Now if I want to pull off my arbitrage shenanigans by selling a sheep in Iran, I'll have to transfer the money back to the US, which in this case means it'll be exchanged at every border along the way. But this series of measurement conversions looks like it's moving. Like, it's an exchange rate particle that gets created in Iran, carries value from Iran to the US, then disappears. Wait, let's see that again. Buy a sheep, bring it to Iran, sell it, money changes from rial to rupee to myriad to rupee to pound to dollar, and I end up with more money than I bought the sheep for to begin with. So that's it. Real standard model physics in your own barnyard. And hopefully now you can see why measuring things differently in different places inevitably gives rise to a long-range interaction mediated by a particle.
Okay, this isn't really the analogy. I just want a 5-second snippet where you see machine gun spraying of photons at electrons. Keep an eye out for it, please.
For example, the electromagnetic potential tells us how electric charge is measured differently at different places. It's the electron exchange rate, and the excitations in the electromagnetic field are particles which we call photons. Instead of transferring monetary value, these photons transfer momentum from one electron to another. And if you add up a whole bunch of these momentum transfers, you get something that we call a force. But isn't a photon a particle of light and not a force? Well, once you have the idea of an exchange particle, you don't actually need the electrons at the endpoints anymore. You could just have that particle moving through empty space on its own. That's why photons are both the particles that mediate the electromagnetic force and bona fide particles on their own. In fact, all the forces we know, like the electromagnetic interaction, the strong interaction, weak interaction, and gravitational interaction, work this same way at a fundamental level. An exchange particle, which physicists crazily call a gauge boson, transfers momentum and energy between two matter particles. And this is what...
All right, that's a better Feynman diagram, because the boson in the middle cannot travel faster than the speed of light, so there has to be even a slightest amount of time in the y-axis. But that's what I just wanted to show you. Let's watch it again. Again, these are virtual. They cannot be measured, nor can they be detected. But the model suggests that these bosons are what is responsible for mediating the force. In this case, the photon is a boson when it mediates the electromagnetic force. Let us get back to drawing stuff, please. So, if you want to be fancy, you can say stuff that is not in the syllabus and say that these particles are those that obey Bose-Einstein statistics and they have a whole integer spin, either 1, 0, or -1. But that's not in the syllabus, but that's the real way, that's the real dichotomy key. Either you have a half integer spin and you obey Fermi-Dirac, or you have whole integer spin and you are obeying Bose-Einstein. Now, let's just get these other bosons together. Now, we've got the Higgs boson, which is thought to mediate the gravitational force. Yeah, prior to Peter Higgs.
Higgs is special, it's
I know. Graviton. And the graviton is theorized to exist. It's quite difficult to detect. In the nuclear, we have the strong nuclear, which is the gluon. And the weak is going to be either your W minus or your W positive boson, or your Z naught boson. Okay? So you've got these ons. Bosons can be photons, gravitons, or gluons. Now, this table, some might say stolen. I like to prefer borrowed from Pearson. It has them in their relative strength. So you'll notice the strong nuclear, if it has a relative strength of 1, then all the rest are getting pretty weak. Okay, so just remember that. The strong nuclear is the strongest. The weak is weaker. But there was a question a couple of years ago that caused a bit of kerfuffle among students, and that was to compare the ratio of gravity with electromagnetic. And it was a multi-choice. There were 4 answers. There's one correct answer. It's D. But then they went, but let's allow 10 to the negative 20 as well. And I had a bit of a whinge, but they just said, nah, if a kid picks this, it's quite weak, and pay it. Now, here's what you do if you ever get that question. What you can do is compare an SI unit of charge. Sorry, try that again. Take 2 electrons and put them a meter apart and compare the gravitational attraction as a ratio of the electric. Sure, why not? Let's do it now. F electric as a ratio of F gravity. We'll do a K, we'll do a Q1, and we'll do a Q2, and we'll divide by an R squared. And since they are both inverse square laws, you're really comparing these values. Now, I'm just going to be lazy and do orders off. So we've got 9 by 10 to the 9. A charge of an electron is about 10 to the negative 19. Well, there's 2 of them, so let's just square it. And then we've got good old Cavendish with his gravitational constant, 10 to the negative 11. And then an electron is about 10 to the negative 30 kilograms. Well, let's square that. Can you see what I'm getting at here? That's 10 to the 10 by 10 to the negative 38 as a ratio of 10 to the negative 60, 10 to the negative 71. Let's tidy it up. 10 to the 28 compared to 10 to the 71, which is roughly 1 compared to, let's drop both numbers down by 28. What are we at? 50, 40, 42, whatever. I'm rounding here. 10 to the 42. That is the relative, negative, Mr. Murray. God damn it. There we go. That is the relative strength of gravity compared to electric when you put 2 electrons next to each other. The answer is D, 10 to the negative 39. Mind you, this scale is comparing from the strong nuclear. So electrical magnetism is already 10 to the negative 2. So if you compare 10 to the negative 2 to 10 to the negative 39, you're comparing 1 is to 10 to the negative 41. And any difference is because I rounded numbers. But that's what you would do to solve a 1-mark question. It's only worth... Unless you remember that gravity is very small. Okay? The easiest example is, look, I can pick this pen up. I am overcoming the entire gravitational force of the planet. And I can do this at my leisure. And the poor gravity, the entire planet is trying to oppose me, and it cannot. Because the gravitational force is piddly. Okay? Now, gluons. These are bosons. Let's just remind ourselves. Bosons that mediate strong nuclear. Okay?
So, what was the Higgs boson?
Ask Ben after class.
As in Ben Beaton.
Yes. So, I've added this. Let's just have a quick look. Ah, yes. My friend Richard Feynman was interviewed. He was a very famous guy, and rightly so. He was interviewed by PBS or HBS or NBC or whoever the hell it was, and they said, if you could go back in time to a dawning civilization that's just created the language and communication, some of you in my Year 9 class might remember this story, and you spawn into existence and you tell them one thing, and then you spawn out of existence. What one thing would you say that would advance this civilization by the most? And he's sort of sitting there. Maybe the question was given prior to the interview. Does anyone remember what he said? Oh,
So we say it in unison.
all right, say it in unison. Unison, ready?
All things are made of smaller
Things that jiggle.
There we go. All things are made of smaller things that jiggle. In that, you have the first three postulates of the kinetic theory, that all matter is made of indivisible atoms in constant motion, colliding elastically. But then, this graph here is his second sentence, because he goes, all right, I want to kind of hit another one. He goes, these little things will repel when you bring them close together, but they will attract when further apart. And in that, in those two sentences, that's my bet on what would advance this civilization by the most. So they can take the first sentence and thermodynamics and chemistry and energy and kinematics and all that. Now, this is a force curve, gentlemen, of the strong nuclear. And there's a sweet spot right here where things are good. All right? That is where you want your nucleons to be so that they can be strongly bound. Please stop talking. I've got lots of stuff to get on with. And in fact, it turns out this is in the order of femtometers. That's just outside the metric prefix table that you are given. We get down to pico. We need to go 10 to the 3 deeper. Femto, that is the relative size of a nucleon. And so you are going to be a femtometer away from your nearest nucleon neighbour, be it proton or neutron in the atom. Okay? And turns out, if you don't believe me, where the hell's that number gone? Turns out, if you don't believe me, the Coulombic repulsion of 2 protons at that distance is 200 newtons. Yes, 200 newtons. That's quite macroscopic. If left to their own, they would go, pa-choo! Were it not for our gluons, these mediating particles that bounce backwards and forwards between proton and neutron that keep everything glued. That's why they were called the gluon. They're the gluey boson that binds our nucleus together. Look at these physicists, they've got senses of humour. So, why do they not fly apart? The answer is provided by this strong nuclear force. But here's the thing, it's not an inverse square. There's no mathematical equation. If a nucleon was to get a slightly bit further apart, then it just drops to 0 and pachoom, it goes flying apart. And that's what determines the nuclear instability. Fission. Remember we said there needs to be just the right ratio of protons to neutrons. You can't just have an atom with 10 protons, because the strong nuclear has to bounce from proton to neutron. Okay? So you need to have a good ratio. And if you get too close, it goes from attraction to repulsion. So it goes, no, stay in your lane, you be there, I'll be here, and we can fire gluons between each other. Okay? But if I take one step away, then you can only fire gluons between your neighbours. I better hope that there's some gluons bouncing for me from some closer neighbours. And that kind of explains why shit happens. If you've just got a jiggling atom, occasionally it just goes and spits out a beta particle. Right? You've just got this chaotic motion, and then unfortunately some probability states that at some time a proton's just going to be too close to another proton and too far from a neutron, and pa-ching, it goes flying apart. So, they're our gluons. Gluons mediate strong nuclear. They have never been directly identified. So could we just... Murray Gell-Mann. He's a good bloke. Gell-Mann. He proposed them. You don't need to know Murray Gell-Mann. Okay. They're very short range. They are mediators of the strong nuclear force, and there is compelling indirect evidence, as is most evidence on the atomic scale. Atoms are thought to exist. Indirectly, we have observed them. Okay, so there's not much of a step to say that gluons exist. We're confident that atoms exist. We're also confident that gluons exist. Okay? So, if we just go back to the top of our Satyendra, let's just go bosons, force mediating particles. They're virtual particles that mediate. So it is a little bit of stamp collecting here. We need to now remember the four fundamentals and list them in rank of weak or strong to weak, short range, long range. Now we're going, okay, are you a boson that mediates one of those forces, or are you a fermion? Look at him, Enrico Fermi. You might have seen him in such Year 11 textbooks as Heinemann Stage 2 Physics. No, because you've got the new textbook. He was pretty big in nuclear physics, Enrico Fermi. He developed the first fission reactor with graphite and fissile material. Now, fermions, they are our particles that have mass and can be detected, and this is what all matter is made of. So right now, I'm looking at you, I'm looking at fermions. Okay? It's not in the syllabus, but to correctly identify them, you would say that they have half integer spin and they obey Fermi-Dirac statistics. Now, more on Dirac in just a moment. We're going to get to a table at the bottom of this page. We also have here Wolfgang Pauli, very handsome gentleman he is. Now, fermions are associated with matter. So, you know, we could... Fermions usually associated with matter. They obey Pauli exclusion principle. So, for example, electrons are fermions. You are made up of protons, quarks, electrons. There's a rule that says that these fermions cannot exist in the same space and have the same quantum number. So, spin. This is talking about your spin up and your spin downs of electrons that exist in orbitals. If you've done it in chemistry, that's your whole S shells, P shells, D shells, and stuff gets weirder and weirder. But suffice to say, I have some fermions on the surface of my hand that cannot exist in the same space as the fermions in the surface of the table. So my spin-up fermions can't be in the same space as the table spin-up fermions. Prevents them from falling through, and they repel each other with the electromagnetic force. Bosons might be involved here. This is this weird thing. Forces now, if I'm pushing myself on the table, I'm actually transferring bosons, like laser beams. And they're imparting momentum to the table. Isn't that fun? Remember back to this stadium analogy, that if the atom is a stadium, that the nucleus is a tiny little marble at the centre of the stadium. And this table, all 100 kilos of it, let's just say we've got 10,000 Avogadro's number of atoms. Right? Would you be happy with that estimation? 10,000 Avogadro's numbers of atoms, yet this table is mostly empty. It is mostly empty, but it doesn't let light through, nor does it let other matter through. Okay? So just remember that. So Pauli, his exclusion principle, also supported this. All the science coming together and agreeing. Okay, now, this is our first split. You're either a lepton, so fermions can be split into leptons or hadrons. Now we are going to look at leptons from the Greek word leptos, meaning small or light in mass. Okay. Now, this group of particles, they can interact by exchanging W and Z, which mediate the weak nuclear, but they can also interact by exchanging photons, which mediates the electromagnetic force. And they also interact with gravity. Okay? So gravitons to mediate gravity. Okay? So just remember that. Electrons have mass, and gravity would pull them towards the surface of the Earth. Multiply the mass by 9.8, that's your approximate weight of an electron. But Very good pub quiz question. They do not interact with the strong force. They do not interact via the strong. So gluons, no. In fact, let me write that. Okay, so let's get back to that dichotomy. All right, our electrons, they will interact with 3 of the 4 fundamental forces. Gravity, electromagnetism, and the weak nuclear, but not the strong nuclear. Okay. Now, let's get down to our family of leptons. I would like you to do the following. We're going to slice this along here and call these guys stable. For most part, we exist in a generation 1 lepton family. It turns out the heavier you get, the more energy and mass you have, the more unstable you are. So let's just talk about our generation 1 Pokemons. We said that we have an electron. Now an electron is a lepton and it has its associated electron neutrino. And we learnt about the neutrinos when we did beta decay. Ooh, something's going on with the weak nuclear force and our leptons here. Now, if you are a lepton, we're going to assign you a special number that has to be conserved in nature, and that's lepton number. And if you're a lepton, you've got a lepton number of 1. Okay? And for the electron, we already worked out that it's got a mass of 0.511 MeV on c squared. That's how much energy you would need to make that amount of matter. Now, Dirac was playing with his equation. Was it the Dirac equation, or was he playing with Schrodinger's? Dirac first was playing with some maths. I don't know what maths it was, but the mathematics came out that there was a positive value answer and then there was a negative value answer. And this equation, the Dirac equation, was talking about particles. So he went, this is weird. The math said that there's a positive answer and there's also a negative answer. What would that mean in the real world? And so he goes, all right, maybe the negative answer is the opposite of matter. Maybe it is antimatter. And sure enough, you get your antiparticle is the positron. Now the positron, his little buddy, is the anti-electron neutrino. And they have lepton numbers of -1. There's rules, and I'm running out of time to explain these rules. This lepton number must be conserved in all particle interactions. Yes?
So positive 1, 2, 3 and negative 1, 2, 3.
No. No. 1, 1, 1 and -1, -1, -1. Now, if you get more mass, and I'll tell you now that you are pretty much built with generation 1 leptons and hadrons. Gen 2 and Gen 3 are just too heavy and too unstable, and they don't like existing, and so they will just explode and spit out their extra energy and mass. But the second gen lepton needs 106 MeV on c squared, and if you can do that, you make a very heavy electron, which we call the muon. Now the muon we've already experienced. The muon is a very high energy lepton that is created in the upper atmosphere by collisions of cosmic rays, and in a stationary rest frame they exist for 6 microseconds before they spit off other energy and matter and decay into smaller forms. So we've already encountered the muon, but with the muon we have the mu neutrino, also a lepton. And so Paul Dirac said, well, hang on, there must be an anti-muon, which is the mu plus, and his associated anti-mu neutrino. They are anti-leptons. Oh, by the way, I should put up the top here. I've color-coded this for a reason. Matter, the antimatter. And I would appreciate just 2 more minutes just to get us to the same spot as the other class. If you go into your level 3 gen lepton, you need 1,000 777 MeV, so we're up to a 1.7 giga electron volt per c squared. Wouldn't you know that we would be producing a tauon, which is a tau negative, and his associated tau neutrino. And then we have also observed the antimatter is going to be the anti-tau, or the anti-tauon, with his anti-tauon neutrino. That there is the Greek tau. That there is the Greek mu. That there is the Greek... Lambda? I don't know. It's a Greek. It looks like a squiggly V, but it is not a V. It is a Greek character. Now, just on the neutrino, I just want to quickly explain the neutrino. The neutrino is very light, because they'd already, in 1932, Chadwick said, I'm going to call this sucker a neutron. It was a neutral particle in the nucleus with a mass of about 1,000 MeV on c squared. But then they cut forward to, 20 years later, they discovered the neutrino, a much, much smaller, much, much lighter. And so they adapted the ino in Italian. If you chuck ino at the end, it means smaller version of. So the neutrino is the very small neutral one. Very light, very small neutral one. And really, its mass energy is so small that it doesn't really factor into mass equations. If you look at how much energy it actually has, it is not significant. And that's actually what took so long. That's why it took so long for it to be detected, is because you could not figure out that there was a missing mass. When this little neutron spat out at 99.9999999% the speed of light, no one really noticed because it was so insignificant. But before you go, please, I know you all have nowhere to be, so please. Let's look at this equation. This is called annihilation. Annihilation of matter and antimatter. Albert Einstein said that if we could combine matter and antimatter, then you would produce energy equal to m0 c squared. Now, we've already looked at some conservation laws. In year 11, you would have said that mass number, it must be conserved. So if we looked at a chemical equation, you've got 0 and 0. That's the mass number is the number of nucleons. And over here we've got 0. So we're good there. And then in year 11, you might have done charge. Well, let's have a look. We've got a -1 charge and a +1 charge. Well, gamma rays, no charge. So we've got a net 0 charge there. Momentum is also conserved. So we might have momentum this way and then momentum that way, and then we'll have 0 momentum over here, because remember, your two gamma rays travel off, if you can recall, at 180 degrees to each other. Do you remember that? Yes. They travel off with the same momentum, and hence same energy, and hence same wavelength, and hence same frequency, but 180 degrees in the opposing direction to conserve momentum. Isn't that lovely? That just occurs. Next, your mass energy equivalence must be conserved. So if I've got a 0.511 MeV on c squared there, and a positron is also 0.511 MeV on c squared, we must produce two gamma rays, each with energy of 0.51 MeV on c squared. And sure enough, we do. That's PET scans, if you can recall positron emission topography. 0.5 MeV, that means that this photon is in the gamma range. Okay? There is so much energy being produced into a ripple of electromagnetic disturbance, we call it a gamma ray. Okay? And it will always be a gamma ray, and it will always be a 0.511 eV, and you can figure out its wavelength at home for homework. Last thing, the lepton number. Now, this is what they said. In order for us to make sense of these particle interactions, we're going to assign him as a lepton, and him as a baryon, and him as something else. This number must be conserved. So they made an extra rule. So let's have a look. An electron has a lepton number of 1. An antilepton has a lepton number of -1. And if you're anything else, you've got a lepton number of 0. Anything else, a quark, a proton, a gluon, a photon, 0. And that works. That is why this can occur. Okay? This also explains to all of you kids in just a week's time. The kid that goes, oh, why is it an anti-electron being formed when we spit out a beta negative particle? It's to conserve lepton number. That's it. That's it. There's a law in science that says that in particle interactions, lepton numbers must be conserved, hence the anti-neutrino for every beta negative particle. Much more on that next week.
So how does one prove? How